Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to start talking about trigonometric identities and how to prove them. I believe proving trigonometric identities is one of the areas that students encounter in math that causes a great deal of stress. And it's similar to word problems because when you're asked to prove these identities, you don't necessarily know where to start, and there's often more than one way to do the proof. And although I'm not going to be able to give you a set procedure to follow every time, I'm going to give you some recommendations and some suggestions for strategies that will help you get going with them. The thing that I want to point out with identities is, although there's an equal sign, you're not solving an equation. When you're proving an identity, you're making one side of the equation, either this side or the right-hand side, identical to the other side. And that means you can only manipulate the one side you're working with. When you're working with that one side, it has to remain equal. I often see students start moving things back and forth and doing things to both sides. That's a strategy we use when we're solving equations, and we're going to get to trig equations after trig identities. But with trig identities, you're doing a proof. So you want one side, you want to go through logical steps using correct methods to make one side equivalent to the other side. And to do that, we're going to be looking at some basic identities and using those, and using different algebraic techniques as well. So the best way to do this, I think, is just look at a variety of examples. I'm going to be grabbing examples from this textbook, Basic Technical Mathematics by Alan J. Washington. I want to start off by introducing some basic identities. Some of them we've talked about already, and I want to expand on those because we're going to be using these identities to do proofs. We're going to start off with the reciprocal trig functions because we've defined those already. So the first one, cosecant of theta, is the reciprocal of the sine function. Secant theta is 1 over cos theta. Cotangent theta is equal to 1 over tangent theta. We've looked at these in a previous video, but we're going to also look at rewriting these so that I can define sine theta as the reciprocal of cosecant theta. Similarly, cosine theta is the reciprocal of secant theta. And tangent theta is the reciprocal of cotangent theta. The easier you recognize these, the easier doing the identities will be. So spend some time getting comfortable with these. Maybe start by making a list of identities and just keep adding to it as we go. And the practice of even writing that out will help you become more familiar with them. Let's take a look at some more identities. There are some more basic trig identities that we're going to be using quite often. And what I want to do is show you where they came from. And I'm going to use my right triangle with an angle theta. And I know that the adjacent side is x, the opposite side of this right triangle is y, and the hypotenuse is r. If I were to take the ratio sine theta over cos theta, and then write each of those trig functions in terms of the ratios of how they're defined. So sine theta would be y over r, opposite over hypotenuse. Cosine would be adjacent, which is x, over hypotenuse, r. And then I could express that's dividing y over r divided by x over r. My rules of algebraic fractions say that I can do the division by multiplying by the reciprocal. The r's will cancel, and I will end up with y over x. If I go back to this relationship, the ratio y over x, opposite over adjacent, is also defined as tangent. So that gives us our next basic identity. Continuing with the numbering system, tangent theta is equivalent to sine theta divided by cos theta. I could do the same thing, taking the ratio of cos theta divided by sine theta. Cos is adjacent over hypotenuse, so x over r. Sine of theta is the ratio of opposite over hypotenuse, so y over r. And that would be x over r divided by y over r. My rule of dividing fractions is I multiply by the reciprocal. I can cancel the r there in the numerator, the r there in the denominator, and I'm left with x over y. And we know the ratio of adjacent to opposite is also defined as cotangent. So therefore, that's our next basic identity. The cotangent of theta is also equal to cos of theta over sine of theta. And these are going to be very useful identities when we're proving other identities. So again, add those to your sheet of identities, get familiar with it, recognize it so that you know that it's something that you can use when you're doing your proofs. We have 3 more basic identities, and they're called the Pythagorean identities. And I'm going to use this right triangle again, and I'm going to show you where they came from. Another thing I know about right triangles is the right triangle theorem, which tells me x squared plus y squared is equal to r squared. What I'm going to do is I'm going to divide both sides of the equation by r squared, which means I'm going to divide every term by r squared. And then I'm going to express this as x over r squared. I can express this as y over r squared. That's going back to laws of exponents that I covered in a previous video. And r squared over r squared is 1. Then what I'm going to do is I'm going to express x over r as a trig function. Adjacent over hypotenuse is cosine. So this will be cosine of theta squared. And the same thing here, opposite over hypotenuse is the same thing as sine theta. So this is sine theta squared. And one thing that I want you to understand is that it's acceptable to use a notation for indicating squares of functions where we don't need those brackets. And that notation looks like this. If I have cos theta and I've got the squared, what that means is the cos function is squared. If I wrote cos of theta squared, that means something totally different. That just means theta squared. But by putting that exponent inside, that's telling us that the cos of theta is squared. We do the same thing here. This is sine squared theta. And this is actually our first Pythagorean identity. So I took this right triangle theorem in relation to this right triangle. I divided both sides by r squared, and then I changed my ratios to the trig functions they represented, and that gave me my first Pythagorean identity. Cos squared theta plus sine squared theta equals 1. If I took this same right triangle theorem equation and I divided through by x squared, both sides, which means every term, x squared over x squared would give me 1. Y squared over x squared would be y over x squared. Y over x is tangent theta, so this would be equal to tangent squared theta. And if I had r squared divided by x squared, that's the secant ratio, so this is equal to secant squared theta. To get my third Pythagorean identity, I divide both sides by y squared, which means I divide every term by y squared. So when I divide this by y squared, x over y ratio is equal to the cotangent theta. So I'll get cotangent squared theta. Plus y squared divided by y squared is equal to 1. and then r squared divided by y squared. R over y is cosecant theta. So that's how I get that term. So these three are called my Pythagorean identities. We're going to use these 11 identities in proving other trig identities. So let's do one example in this video and then we'll continue on in the next video. So it's a good idea to have your basic identities handy so that you can be referring to them as you're doing your proofs. And I left out 3 of them. I left out the opposite of each of these. So we know cosecant theta is equal to 1 over sine theta. Similarly, sine theta is equal to 1 over cosecant theta. So I can see both of those identities in that one. Similarly, secant theta is equal to 1 over cos theta, and therefore cos theta is equal to 1 over secant theta. Cotangent theta is equal to 1 over tan theta. Similarly, tan theta is equal to 1 over cotangent theta. So I just, because of room, I didn't write those next 3. And then I wrote tan theta is equal to sine theta over cos theta. Cotan theta is equal to cos theta over sine theta. I showed you where those came from. And then here's our 3 Pythagorean identities. So this is our first proof. And when you're asked to do a proof, as I mentioned, you just work with one side of the proof and manipulate it, keep it equivalent until you get what's on the other side of the equation. And the nice thing about proofs is you know what the answer is. You know what you're looking for. Generally, I start with the bigger side, the more complicated side, and then I try to simplify it to the simpler or the shorter side. But you can do either, you can work with either side of your equation. And this is my shorter side or my simpler side. So I'm going to take this and manipulate it until it looks like that. So one of the first strategies that's very useful when you're doing trig identities, especially when you've got all these reciprocal ones and so on, is just try to write everything in terms of sine and cosine. So that's how I'm going to start. I know cotangent is, I want to write it in terms of sine and cos. So it will be cos theta over sine theta times secant theta, I know is equal to 1 over cos theta. I'm not going to do anything over here. I'm going to just manipulate this. So this is going to just stay cosecant theta. Now I'm multiplying fractions. I can cancel the same factor in my numerator and denominator. So I'll end up with 1 over sine theta. I don't want to leave it. I do know that 1 over sine theta is equal to cosecant theta, but to do a proof properly, you want to finish this until it's equivalent to the other side. Once you've got that far, then you're done. So you've taken this and you've manipulated it to an expression that's identical to the other side. That's how a proof is done. Let's take a look at more examples on the next video.